Now we will begin working some problems from Chapter 3, problems related to stoichiometry. Stoichiometry always deals with moles, so it's very important that you understand the concept of moles. The first question says, how many atoms are in 29.5 moles of atoms? Well, keep in mind that mole can be a number word. The first use of mole is that it is a number word, and 1 mole of particles is equal to Avogadro's number of particles, which is 6.022 times 10 to the 23rd particles. That's an equality, and we can use it as a conversion factor in dimensional analysis. So the 3 steps for dimensional analysis. Number 1, write down what you want to know. I want to know the number of atoms. The number of atoms. So the number of atoms equals. And number 2, start with the given measured quantity, 29.5 moles of atoms. And number 3, apply conversion factors in order to cancel unwanted units. Right now I have it in moles of atoms. I want to know how many atoms I need. So I'm going to put mole of atoms in the denominator. And I know that 1 mole of atoms contains 6.022 times 10 to the 23rd atoms. So that the unit moles of atoms cancels, and I end up in units of atoms. And this calculates out to be 1.78 times 10 to the power of 25 atoms. So I'm using this relationship, Avogadro's number, and that mole is a number word. Look at the next question. A certain gas canister contains this many gas molecules. How many moles of molecules are present? So number 1, write down what you want to know. I'm just going to say the number of moles. Since in both cases we're dealing with molecules, I just want to know the number of moles. I'll start with the given measured quantity, 4.82 times 10 to the power of 18 molecules. Now remember that the abbreviation for mole is MOL, and so we can't abbreviate molecule MOL. You have to be careful about that or you'll get yourself confused. A good abbreviation for molecule is MOLEC. So this is the number of molecules, and I need to go from molecules to moles. How can I go from molecules to moles with Avogadro's number? There are 6.022 times 10 to the 23rd molecules. So I'll put molecules in the denominator, so the molecules will cancel, for every 1 mole of molecules. 1 mole of molecules contains 6.022 times 10 to the 23rd molecules. So the unit molecules cancels, and I end up in moles, and the number of moles calculates out to be 8.00 times 10 to the negative 6 moles. So there are 8.00 times 10 to the negative 6 moles of molecules present. Okay, question number 3. How many molecules of glucose, C6H12O6, are present in 25 grams of glucose? Now, the first thing that I need to do, if we're given the mass of glucose, I need to go from grams to moles. And the way that you go from grams to moles is with molar mass. So I need to know the molar mass of glucose. The molar mass of C6H12O6 is equal to, and starting with carbon, I have 6 carbons, 6 times 12.011. So on the periodic table, we look at carbon on the periodic table, and carbon is element 6 on the periodic table. And since it's element 6 on the periodic table, the atomic weight is 12.011. So there are 6 carbons, 6 times 12.011, plus there are 12 hydrogens. 12 times, and the atomic weight of hydrogen is 1.008. 1.008 if I keep 4 significant figures. This periodic table only has 3 significant figures, but if I keep 4, it'd be 1.008. And next, I'm going to have 6 oxygens, plus 6 times, and oxygen, the atomic weight of oxygen is 15.9994, and if I round it to 4 significant figures, I get 16. So the easiest thing to do is to just round everything to 4 significant figures. I should have done that here to 12.01. 4 significant figures, and then when I add everything up, just round it to 4 significant figures, and I'll get 180.2 grams per mole. That's the molar mass of glucose. Now, one suggestion that I have for you is that instead of writing it down whenever you work this kind of a problem, I would recommend that you simply add it into your calculator. You can put it in your calculator twice or even 3 times faster than you can write it down. Just in your calculator using the periodic table, you would say 6 times 12.01 plus 12 times 1.001 plus 6 times 16 equals, and you get 180.2. And that's the fastest way to get the molar mass. So there's the molar mass. So with the molar mass, now we can solve the question that's asked. This says how many molecules of glucose. So I want to know the number of molecules. The number of molecules. And I'm going to start with the given measured quantity. I have 25.0 grams of C6H12O6. And the first thing that we will do is to convert from grams to moles. Now, how do we go from grams to moles? We go from grams to moles by using the molar mass. We go from grams to moles using the molar mass. The molar mass of glucose, we just determined back here, is 180.2 grams of C6H12O6 for every 1 mole of C6H12O6. So that's the molar mass. We got it off of the periodic table. Always go from grams to moles using the molar mass. So the grams of glucose cancels, and now I have it in moles of glucose. Next, we're going to go from moles to molecules. 1 mole of glucose, C6H12O6, which I put in the denominator so it will cancel, contains 6.022 times 10 to the 23rd molecules. So I'll abbreviate molecules that way. So moles of C6H12O6 cancels. I end up in molecules, and the answer, when this calculates out, it will be 8.35 times 10 to the power of 22 molecules. Okay, so we went from grams to moles using the molar mass. Once I had it in moles of glucose, I went from moles of glucose to molecules to the number of particles using Avogadro's number. Okay, question number 4. What is the molar mass of ammonium nitrate? Now notice that you cannot even answer this if you don't know the formula for ammonium nitrate. In Chapter 2, we learned how to go from the name to the formula. So you have to be sure that you review that and you know what ammonium nitrate is. Well, the ammonium cation, if we just write it down over here, the ammonium cation is NH4 plus 1. The nitrate anion, which you just have to memorize, you can't get this easily off the periodic table, nitrate is NO3 minus 1. So what is the formula of ammonium nitrate? Well, it's got to be electrically neutral. For every positive, there's got to be a negative. And this is plus 1, this is minus 1. So ammonium nitrate has the formula NH4NO3. So the molar mass of ammonium nitrate, capital script M, stands for molar mass. And in chemistry, for some reason, we write everything as a subscript. When I say the molar mass of ammonium nitrate, NH4NO3 is ammonium nitrate, equals, and I have to take into account all of the atoms here. Now I have 2 nitrogens, and from the periodic table, the atomic weight of nitrogen is 14.01. So 2 times 14.01 plus, there's 4 hydrogens. And 4 hydrogens, let's just go ahead and put 4 times 4 times 1.01, because that's what we have on this periodic table. Plus, there's 3 oxygens, 3 times 16. And when we do this, we can just round this to 4 significant figures, and we'll always be correct here. We get 80.05 grams per mole. 80.05 grams per mole is the molar mass. So be sure you know how to go from the name to the formula that we practiced in Chapter 2, and then we can easily get the molar mass in that way. Okay, question number 5. What is the mass in grams of this many water molecules? So we're going to follow the 3 steps. Number 1, write down what you want to know. I want to know the number of grams of water. The number of grams of water equals. Number 2, start with the given measured quantity, which is 3.77 times 10 to the 10th water molecules. 3.77 times 10 to the 10th H2O molecules. So number 1, write down what you want to know. On the left side of the equal sign, put the number sign in the unit you're looking for. equals, and number 2, start with the given measured quantity, include the unit. The whole point of dimensional analysis is you include the unit. And then number 3, apply conversion factors. If I don't know anything else to do, I'm going to put water molecules in the denominator, H2O molecules. And here's what I know. I know I can go from molecules, which are individual particles, to moles using Avogadro's number. 1 mole of water consists of 6.022 times 10 to the 23rd water molecules. Okay, so that gets me from water molecules to moles of water. Now I have it in moles of water, and we want to know how many grams of water. To go from moles to grams, we use molar mass. So I'm going to say times, draw a line, and put mole of water in the denominator. And 1 mole of water has a mass from the periodic table of 18.02 grams of water. Be sure that you know where I got the molar mass from. I got the molar mass because I had said 2 times 1.01 plus 16 equals 18.02. So moles of water cancels, and I have it in grams of water. And this calculates out to be 1.13 times 10 to the minus 12, 1.13 times 10 to the negative 12 grams of water. So knowing the number of particles, we're able to get the mass by converting particles to moles and then using molar mass. Okay, so far we've not had to use any mole-to-mole ratios. Problem number 6 is the first one that we're doing here where we have to use a mole-to-mole ratio. And problem number 6, how many carbon atoms are present in this much glucose? Okay, so I'll show you where to use the mole-to-mole ratio, but let's just start off following our 3 steps. Number 1, write down what you want to know. I want to know the number of carbon atoms. The number of carbon atoms equals. Number 2, start with the given measured quantity, 10.0 grams of glucose, and write the formula, C6H12O6. Now notice, this is our first true stoichiometry problem. A stoichiometry problem always gives you the amount of one substance, in this case 10 grams of glucose, and it asks for the amount of a different substance. In this case, it wants to know how many carbon atoms. Carbon atoms is not the same as glucose. Carbon is in glucose, but they're not the same. If you're given the amount of one substance and you're asked about the amount of another substance, that's a stoichiometry problem, and you have to wake up screaming mole-to-mole ratio. So the first thing I've got to do is convert grams to moles. Now at the top of the screen, I think that I can fit it all in. At the top of the screen, I can't quite get it all in, but here at the top of the screen you can see the molar mass of glucose, which we calculated earlier. 180.2 grams per mole is the molar mass of glucose. So I'll use that for question number 6. Question number 6, I want to know the number of carbon atoms. I have 10 grams of glucose, so I'm going to go from grams to moles using the molar mass. So in the denominator, I have 180.2 grams of glucose, C6H12O6. Remember, we got this off the periodic table. We worked it out back on question number 3. That's equivalent to 1 mole of glucose, C6H12O6. Okay, so grams of glucose cancels, and we now have it in moles of glucose. The next thing to do is the most important problem in every stoichiometry problem. You wake up screaming mole-to-mole ratio. I'm going to put moles of glucose, C6H12O6, in the denominator, and I need to go to moles of carbon because that's what we're looking for. We're going from glucose to carbon, moles of carbon. Well, where do we get the mole-to-mole ratio? In this case, we get it from the formula itself, from the subscripts of the formula. There are 6 carbons per every glucose molecule, or there are 6 moles of carbon per every 1 mole of glucose. This is the mole-to-mole ratio that we get from the subscripts of the chemical formula. Okay, so as we work this then, I want to know the number of carbon atoms. I'll say times, draw a line, and I'll put the number of carbons here will be 1 mole of carbon contains 6.022 times 10 to the 23rd carbon atoms. 1 mole of carbon contains 6.022 times 10 to the 23rd carbon atoms. So this is Avogadro's number. So now moles of glucose canceled and moles of carbon canceled. So now I have it in carbon atoms. So I went from mass to moles using molar mass. Then I went from moles of one substance, glucose, to moles of another substance, carbon, using a mole to mole ratio. Now that it's in moles of carbon, I can get the number of carbon atoms, which is what this asks for. How many carbon atoms? And so when I've got to get Avogadro's number correct. Let's say times 10 to the power of 23 carbon atoms. 6.022 times 10 to the power of 23 carbon atoms. And that calculates out, let's just write it here. That's equal to 2.01 times 10 to the power of 23 carbon atoms. 10 to the power of 23 carbon atoms. Be sure that you are practicing the calculation and making sure you're getting the correct answer as you do this calculation. So this has a mole-to-mole ratio. Okay, number 7 gives us the density of chloroform. CHCl3 is chloroform. This is the density. By the way, notice that you are not expected to know the formulas for organic compounds. Back on number 6, this is glucose, and I gave you the formula for glucose. If you were to take organic chemistry, you would learn how to get the formula. But at this level, glucose, I will give you the formula. I'm giving you the formula for chloroform, CHCl3. So you don't have to memorize the formulas for organic compounds. This is the density of chloroform. How many chlorine atoms are present in 2.5 microliters of CHCl3? Now, microliters, this is a unit of volume. This is a unit of volume. And we're given the density. Okay, well, remember that we can use density as a conversion factor. We can use density as a conversion factor in this case. So this is the density, which we can use as a conversion factor. Now let's just set this up as a dimensional analysis problem, and it will solve itself. Number 1, write down what you want to know. I want to know the number of chlorine atoms. The number of chlorine atoms equals. Number 2, start with the given measured quantity. The given measured quantity is, we'll have 2 numbers. Which do I start with? Now, all along, I've been saying, number 2, start with the given measured quantity. And what I'm trying to emphasize is you never, never, never start with a conversion factor. And density can be used as a conversion factor. This is the given measured quantity, 2.5 microliters. Density is a conversion factor. I don't start with it, so I start with 2.5 microliters. Now, I've got to get microliters to liters. There is a shortcut that I can use here. You have to know the table of metric prefixes, and you have to know that micro means times 10 to the negative 6. So I'm going to write 2.5 times 10 to the negative 6 liters, because this is another way of saying microliters. This is another way of saying microliters, times 10 to the negative 6. So this is the Greek letter mu. It stands for micro, 10 to the negative 6. Next, I need to get liters to cubic centimeters. So I'm going to say times, draw a line, and I know that 1 liter contains 1,000 cubic centimeters. 1 liter contains 1,000 cubic centimeters. 1 liter contains 1,000 milliliters, and a milliliter is the same as a cubic centimeter. So that liters cancels, and I have it in cubic centimeters. Now, the next thing I'm going to do is I'm going to use density as a conversion factor. There's 1.492 grams of CHCl3 for every cubic centimeter of CHCl3. Okay. Here I'm using density as a conversion factor. So right here at this step, I'm using density as a conversion factor. Now, you could solve this as a plug-and-chug problem, because density as a conversion factor, because density is equal to mass over volume. I'll just write that over here. Density is equal to mass over volume. You're given the volume in microliters. You know the density. You calculate the mass. But in this illustrates that it's often faster and is a shortcut to use density as a conversion factor in dimensional analysis. Okay, so the units of cubic centimeters cancels, and now I have it in grams of chloroform. Well, once I have it in grams, I always convert from grams to what? I go from grams to what? I go from grams to moles. So I'm going to go from grams of CHCl3 to moles of CHCl3. CHCl3. And in order to do that, I need to use the periodic table. And from the periodic table, I can get the molar mass. Now, I'm not even going to write this down. I'm going to use my calculator. So I'm going to plug directly into my calculator. I've got one carbon, so 12.01, plus one hydrogen, 1.01, plus there's 3 chlorines, 3 times 35.45. And I hit equals. So you do that directly in your calculator. You don't have to use parentheses or anything. Your calculator knows the hierarchy of operation. So again, I would put 12.01 plus 1.01 plus 3 times 35.45. And that gives me 119.4 grams of chloroform per mole. So this is the molar mass. Now, the next step is the key step in every stoichiometry problem. Look, this is asking about how many chlorine atoms, but we don't have chlorine, we have CHCl3. Anytime you go from one substance to another substance, we're going from CHCl3 to chlorine. Anytime we go from one substance to another substance, we need to wake up screaming mole to mole ratio. So in the denominator, I'm going to put moles of CHCl3. And in the numerator, I need to know the moles of chlorine. The moles of chlorine over here. So I'll put moles of chlorine. So what is the mole to mole ratio? Well, I get it from the formula itself. In 1 mole of CHCl3, there are 3 moles of chlorine. 3 moles of chlorine per every 1 mole of CHCl3. So this is the mole to mole ratio. Don't forget that. This is the most important step. This is the mole to mole ratio. And in this case, you get the mole to mole ratio from the subscripts of the chemical formula. So I look back here. Am I getting closer? Now, this is why I always write down what I want to know. In a long problem like this, it's helpful if I can quickly identify what it is that I'm looking for. I'm looking for the number of chlorine atoms. Now, I'm almost there. I have it in moles of chlorine, but I don't have it in chlorine atoms. How do I go from moles of chlorine to chlorine atoms? I do Avogadro's number. So I'm going to say times, and in the numerator, 6.022 times 10 to the 23rd. I don't have space on my page to write chlorine atoms per 1 mole of chlorine. But this is the number of chlorine atoms. And so this will calculate out to, everything in the numerator you multiply, everything in the denominator you divide, and you ignore ones. And when you do that, the number of chlorine atoms that you calculate out will be 5.6 times 10 to the 19th, 10 to the power of 19 chlorine atoms. Now notice that in this case we are limited to 2 significant figures because our given measure quantity only had 2 significant figures. So that's number 7. Okay, question number 8. Now, there's 2 places to get mole to mole ratios. One is from the subscripts of chemical formulas, and that's what we saw in numbers 6 and 7. In questions number 6 and 7, all we had were the formulas of compounds. So C6H12O6, there's 6 moles of carbon per 1 mole of C6H12O6. Chloroform, CHCl3, there's 3 moles of chlorine per 1 mole of CHCl3. But that's one place to get mole to mole ratios. It's from the subscripts of chemical formulas. So there's 2 places to get mole to mole ratios. One is from the subscripts of chemical formulas. But the second place is to get them from the coefficients of balanced equations. From the coefficients of balanced equations. And you have to be able to write the balanced, you have to be able to balance an equation for a chemical reaction. Okay, so let's practice balancing some equations here. So first of all, this is an example of an equation that you have to balance just based on words. Now, if you don't know the names of the compounds, then and you can't go from the name to the formula, then you will not be able to solve this. So be sure that you know how to go from the name of the compound to the formula. So silver nitrate. Now, in this particular case, I know that silver is Ag plus 1. how do I know that silver is Ag plus 1? It's an ionic compound. Well, it's because everything in group 1 has a plus 1 charge. Everything in group 2 has a plus 2 charge. And aluminum has a plus 3 charge, plus 1, plus 2, plus 3. But in this diagonal, aluminum is plus 3, zinc is plus 2, silver is plus 1. So the charge of the silver cation is plus 1. That's silver. And then nitrate is NO3 minus 1. You just have to memorize that. There's not an easy way to get that off of the periodic table. Okay. So the formula for silver nitrate is AgNO3. So I'll write that on the reactant side. AgNO3. For every positive, there must be a negative. So when I write the overall formula, here's the formula for silver nitrate. It reacts with, so I'm going to put a plus here. Silver nitrate reacts with aluminum sulfate. Now, aluminum, I go to the periodic table, aluminum has a plus 3 charge. So Al3 plus. And sulfate is one of those 8 ions that you have to just memorize. SO4, 2 minus, is sulfate. So to get the formula for this, the easy way to get the formula is to crisscross this. So the formula for aluminum sulfate is Al2 parentheses SO4 3. I need the parentheses because I have more than one of the polyatomic sulfate ion. Okay, so that's aluminum sulfate. It says silver nitrate reacts with, so I put plus, aluminum sulfate, here's aluminum sulfate, to form. Now when you see the word to form, we'll put the reaction arrow. So these are reactants, and what is formed will be on the product side, to form silver sulfate. Now silver sulfate, I've got the silver cation and the sulfate anion. So what's the formula for silver sulfate? Well, sulfate's minus 2, silver's plus 1. So silver sulfate is Ag2SO4. Okay. Now let's break this down again. Here's silver, Ag plus. Here's sulfate, SO4, 2 minus. So that's why I need 2 silvers per each sulfate. So it reacts to form silver sulfate. This is the formula for silver sulfate. And aluminum nitrate. So aluminum nitrate, remember aluminum is Al3 plus and nitrate is NO3 minus 1. So the neutral formula, in order for this to be overall electrically neutral, I've got to have 3 nitrates. So I'm going to say plus Al parentheses NO3 close parentheses 3. So that's what this sentence gives us. If you can go from the names to the formulas, you can write this much. Silver nitrate, AgNO3, reacts with, so I'll put a plus, aluminum sulfate, Al2SO43, to form, so I put the arrow, silver sulfate, which is on the product side, that's what we form, and aluminum nitrate, AlNO3. So there's the compound. Okay, so or there's the reactants. The reactants are over on this side, and the products are on this side. So we have reactants over here, and we have products over here. Now in this case, did you notice that all we did was swap ionic partners? I have silver cation on this side, silver cation over here. Nitrate on both sides, aluminum on both sides, sulfate on both sides. So the easiest thing in order to balance this is to underline the ions. And my dumb suggestion when you balance an equation is that you underline the ions as you go. So as we look at this, I have 1 silver and 2 silver. So I'm going to put a coefficient of 2 here. Okay, that balances the silver. Then I have 1 nitrate on the reactant side, but there are 3 nitrates over here on the product side. Well, this already has 2, so that tells me that I did this incorrectly. And so that's one reason that I underline things. If there's 3 over here, then I'm going to have to take that into account. There'd have to be, in order to use the smallest whole number coefficients, I'm going to need a total of 6 over here. Okay, so I'm going to just cross this out. 6 is the coefficient. 6 silvers, and then 3 times 2 gives me 6 silvers. So now silver is balanced. 6 nitrates, and so over here I need 2 times 3 gives me 6 nitrates. Okay. Now I hope you can see why I had to use 6 here. It's so that both the silver and the nitrate would cancel. Now when I come over here, this says I have 2 aluminum and we already have 2 aluminum right here, and 3 sulfate, and this coefficient 3 says there's 3 sulfates. Everything is underlined, and so now everything is balanced. Now notice how the question is worded. On a multiple choice exam, I like to word questions this way. What is the coefficient on silver nitrate when this equation is balanced using the smallest whole number coefficients? And so the answer is 6. The answer is 6. Because this is the coefficient on silver nitrate when everything's balanced using the smallest whole number coefficient. Okay? Now, one of the kinds of reactions you have to know for this exam is a combustion reaction. Now, this is the complete combustion of acetic acid, C2H3O2. So, if you have a complete combustion, you have to know what this reaction is. This is very important. Okay? There aren't very many reactions that you have to know what the reactions are, but this will be one of the first ones that you have to know what the reaction is. In a complete combustion, you have either a hydrocarbon, which has carbon and hydrogen, or you have a compound containing carbon, hydrogen, and oxygen. If that's what you have on the reactant side, either a hydrocarbon or a compound containing carbon, hydrogen, and oxygen, then what you have to do in a combustion is you burn it in O2 gas. You burn it in oxygen gas. And in a complete combustion means you have all the oxygen you need, and your only products will be carbon dioxide plus water. That's a complete combustion. Now, if there's not enough oxygen, you have incomplete combustion, and you'll not only get carbon dioxide, you will get some carbon monoxide. You can't balance that equation because the amount of carbon monoxide and carbon dioxide depends on how much oxygen. So the only one I can ask for is balancing equation for the complete combustion of a substance. So the complete combustion, again, that means you have all the oxygen that you need, and you only get carbon dioxide and water. Okay, so let's do that for acetic acid. For acetic acid, we're given the formula. Acetic acid is H2C3, it's HC2H3O2. It's the formula for acetic acid. In a combustion reaction, it burns in oxygen, and the products are carbon dioxide and water. Now, notice I'm leaving some space so that I can write coefficients on here. Now, I have 2 dumb suggestions. One is always save the simplest substance for last. I'm going to save oxygen for last. My other dumb suggestion is underline each element as you balance it. So I'm just going to start on this left side. I have 1 plus 3 is 4 hydrogens. So I have 4 hydrogens on the reactant side, so I need 4 hydrogens on the product side. So 2 times 2 gives me 4 hydrogens on the product side. Okay. Next, I'm going to look at carbon. I have 2 carbons on the reactant side, so I'm going to underline this. So I need a coefficient of 2 on carbon dioxide. That gives me 2 carbons on both sides. Now I saved O2 for last, and I've underlined everything as I come to it. So the question is, what's the total number of oxygens that I have over here? Well, to add up the oxygens, don't forget to use the coefficient. 2 times 2 is 4. I have 4 oxygens here plus 2 more. There's a total of 6 oxygens. 4 plus 2 is 6 oxygens. So I need 6 oxygens on the reactant side. But don't forget this oxygen. It's not been underlined yet. Don't forget this oxygen. So I already have 2. I need 6 to have it over here. So 2 plus what equals 6? 2 plus 4 equals 6. So if I use a coefficient of 2, that will give me a total of 6. 2 plus 4 equals 6 on the reactant side. 4 plus 2 gives me 6 on the product side. And so it's balanced. Now notice how the question was worded. It says, what is the coefficient on oxygen when this equation is balanced using the smallest whole number coefficients? The coefficient on oxygen is 2, so the answer to this question will be 2. The only way you can get that is to actually balance it. You can't look at this and guess what the coefficient is. You have to actually balance it. Now here's one quick check that if you're rusty with balancing equations, you can put on the reactant side and on the product side. We can just build up a table. So reactant side and product side. And I can list the number of carbons, hydrogens, and oxygen because those are the only elements present. So on the reactant side, I have 2 carbons. And on the product side, over here, I also have 2 carbons. So that's balanced. On the reactant side, how many hydrogens do I have? 1 plus 3 is 4 hydrogens. On the product side, how many hydrogens do I have? 2 times 2 is 4 hydrogens. So that's balanced. Now I add up the oxygens. On the reactant side, how many oxygens do I have in all? I have 2 oxygens plus 2 times 2 is 4. 2 plus 4 is 6 oxygens on the product side. On the reactant side, rather. How many oxygens do I have on the product side? 2 times 2 is 4, plus 2 is 6. And so that's a quick check to tell me that's balanced. All the elements are balanced in that reaction. Okay, let's do another example of balancing a redox, or balancing rather a combustion reaction. The next question says, write the balanced equation for the complete combustion of cyclobutanol. So I'm going to write the formula for cyclobutanol, C4H7OH. Now this says we want to write the balanced equation for the complete combustion of cyclobutanol. That means this will react with what? Well, in a combustion reaction, it burns in oxygen, leaves space. We've got to add in coefficients. And the products in a complete combustion are always what? Carbon dioxide and water. So you have to know that. You have to know what a complete combustion of a compound containing just carbon and hydrogen or a compound containing carbon, hydrogen, and oxygen will be. Okay, so let's balance this. 2 dumb suggestions. My first dumb suggestion is underline each element as it's balanced. My second dumb suggestion is save oxygen for last. It's the simplest compound. It's the simplest substance, I should say, in this equation. And so I can use any equation, even a fractional equation, if I need to. So I'm going to start with 4 carbons on the reactant side, 4 carbons on the product side. I have 7 plus 1 hydrogen is 8 hydrogens. So I need 4 waters. 4 times 2 is 8 hydrogens. Now, how many oxygens are on the product side? 4 times 2 is 8, plus 4 is 12. There's a total of 12 oxygens on this side. 8 plus 4 is 12. Don't forget this oxygen. This is the mistake most people forget. They forget about this, and this is one reason I underline everything. So don't forget this oxygen. So 1 plus what equals 12? 1 plus 11 equals 12. So the easiest thing to do is to say 11 over 2. 11 halves times 2 is 11. So 1 plus 11 is 12. And over here, 8, 4 times 2 is 8, plus 4 is 12. Now this is a fractional coefficient. And the question specified, what is the coefficient on oxygen when the reaction is balanced using the smallest whole number coefficients? So how do I get rid of this fraction? I multiply everything through by 2. And when I do that, I'm going to have 2 C4H7OH plus 11 O2. So I'm multiplying everything through by 2. Forms 8 CO2 plus 8 H2O. That's the balanced equation. And so the answer, the question says, what is the coefficient on oxygen? The answer, therefore, the coefficient on oxygen is 11. That's the correct answer to this problem. So be sure that you can write the balanced equation for the combustion of any hydrocarbon, that's a compound containing carbon and hydrogen only, or any compound containing carbon, hydrogen, and oxygen only. Okay, number 11. Consider this unbalanced equation. Now notice, this is unbalanced, and I emphasized in the test question, these are all old test questions, I emphasized that this is unbalanced. So what's the first thing you have to do before you can solve a question like this? You have to balance it. So I'm going to balance this, and as I go about balancing this, I'm going to save aluminum and hydrogen for last. I'm going to save aluminum and hydrogen for last because they are elements all by themselves, and I can use any coefficient on them, including a fractional coefficient. So with hydrogen, I see 1 hydrogen. I'm going to save hydrogen for last. I'm going to save aluminum for last and hydrogen for last. So that means I'm going to start with chlorine. So I have 1 chlorine on the reactant side, 3 on the product side. So I can underline this and put a 3 here. Now I can balance everything else. But as I look at this, I have 3 hydrogens on the reactant side and 2 on the product side. I can't balance odd and even. So I need to convert this to even. So what I need to do is, instead of balancing this with the 3, let's put a 6 here and a 2 here. See, 6 chlorines, and 2 times 3 gives me 6 chlorines over here. Okay, so now the chlorines are balanced. Okay, and I can balance aluminum then. I have 1 aluminum on the reactant side, 2 aluminums on the product side. So I need a coefficient of 2 right here to balance the aluminum. So I've underlined aluminum, and all that's left is hydrogen. I have 6 hydrogens. How do I get 6 hydrogens over here? I need a coefficient of 3. 3 times 2 will give me 6 hydrogens. Okay. So now everything's underlined, and that is the correct balanced equation. So now we have it balanced. This says how many grams of HCl are needed to completely react with 15 grams of aluminum. Now, one thing that I find helpful sometimes when you have a balanced equation is underneath each substance I can write down what's given and what I need to know. I need to know the number of grams of HCl, so I'm going to put a question mark under HCl. And I have 15.0 grams of aluminum, so 15.0 grams of aluminum. So this is what I want to know. This is what's given, 15 grams of aluminum. So let's solve this stoichiometry problem the way we solve all of our stoichiometry problems using dimensional analysis. So I'm going to start off by writing down what I want to know. I want to know the number of grams of hydrogen chloride, or this is hydrochloric acid, the number of grams of HCl equals. And I'm going to start with the given measured quantity, which is 15 grams of aluminum. 15.0 grams of aluminum. Now, when I have it in grams, I always convert from grams to what? I always convert from grams to moles. And how do I go from grams to moles? By the molar mass. So down here I'm going to put grams of aluminum. I don't want it in grams of aluminum. And the molar mass of aluminum is 26.98 grams of aluminum per 1 mole of aluminum. So there's 26.98 grams of aluminum equivalent to 1 mole of aluminum. So my units of grams of aluminum cancels, and I have it in moles of aluminum. The next thing that I want to do is I don't want it in moles of aluminum, I want it in HCl. So I'm going to say times, draw a line, and put moles of aluminum in the denominator. Well, what do I put in the numerator? Well, this is going to be the mole-to-mole ratio. This is the key step in every stoichiometry problem. This is the mole-to-mole ratio. And here's where it helps if you've written down what you want to know. I want to know the number of grams of HCl. So I'm going to go from moles of aluminum to moles of HCl, because that's what I wanted in. So how do I go from moles of aluminum to moles of HCl? I use a mole-to-mole ratio. And the mole-to-mole ratio, in this case, since this is a balanced equation, comes from the coefficients of the balanced equation. This says that for every 2 moles of aluminum that react, 6 moles of HCl will react. So this is the mole-to-mole ratio. This is the most important thing. You get this from the coefficients in the balanced equation. For every 2 moles of aluminum in the denominator, there will be 6 moles of hydrochloric acid that react. So the aluminum cancels. Now I have it in moles of HCl. Now, I wrote down what I wanted to know. Am I getting closer? Well, I have it in moles, and I need it in grams. So I'm going to say times, draw a line. I'll put moles of HCl in the denominator. Now, how do I go from moles of HCl to grams of HCl? I do it using the molar mass. So use molar mass. Now, notice I also use the molar mass of aluminum back here. Here's the molar mass of aluminum back here. And here I'm going to use the molar mass of HCl. So to get the molar mass of HCl, I go to the periodic table. Hydrogen is 1.01. Chlorine is 35.45. So 1.01 plus 35.45 gives me a molar mass of 36.46 grams of HCl for every 1 mole of HCl. That's the molar mass. That's the molar mass. So moles of HCl canceled. I have it in grams of HCl, which is what I'm looking for. And this calculates out to be 60.8 grams of HCl. Now notice, I'm limited to 3 significant figures. That's what we had back here. But I'm always in the habit of using 4 sig figs for the molar masses. That way I don't get any round-off error. I round down to 3 sig figs. The mole-to-mole ratio is exact. It does not limit me. Based on the equation, that's exact. Okay, so that's the correct answer to number 11. Number 12, what mass of oxygen gas is required for the complete combustion of 10 grams of propanol? Well, the question is, what's the first thing I need For any reaction stoichiometry problem, how can I figure out the mass of oxygen gas for the complete combustion of this much propanol? Well, the first thing you need is you need a balanced equation. And so the balanced equation that I need to get there is a combustion reaction. So this says for the complete combustion. And you have to be able to write the balanced equation for the complete combustion of a compound. Okay, so let's write that equation. I have propanol, C3H7OH. If it is a combustion reaction, it reacts with what? It reacts with O2 gas. And what are the products? Carbon dioxide and water. Now, my dumb suggestion is to underline each element as you've balanced it, and that way you know you're finished with it. And to save oxygen for last. It's the simplest substance here, and I can use any coefficient on oxygen, including a fractional coefficient. So I'm going to start out here for the complete combustion of 10 grams of propanol. I'm going to start out with carbon. I'm saving oxygen for last. I have 3 carbons. I'll put a coefficient of 3 here on carbon. I have 7 plus 1 is 8 hydrogens. So 4 times 2 gets me 8 hydrogens. Now, as I look on the product side, how many oxygens do I have? 3 times 2 is 6, plus 4 is 10. I have 10 oxygens on the product side. How do I get 10 on the reactant side? Well, I've already got 1. Don't forget this oxygen. 1 plus what equals 10? 1 plus 9 equals 10. So right here, I need to use a fractional coefficient. 9 halves, 9 over 2 times 2 gives me 9. So this adds up now to 10 oxygens. So I'm going to have 1 oxygen plus 9 oxygens. 9 halves times 2 is 9. Gives me 10. And 6 plus 4 gives me 10. So everything is underlined. Now, it's harder if we use a fractional coefficient. So my recommendation is get rid of this fractional coefficient by multiplying everything through by 2. And when I do that, this is the balanced equation I will have then. 2 C3H7OH reacts with 9 O2, I'm just doubling all the coefficients, to form 6 carbon dioxide plus 8 waters. So I multiplied everything through by 2. You'll also find it very helpful to write underneath the balanced equation what's given and what you're looking for. You have 10 grams of propanol, C3H7OH, so I'm going to put 10 grams of this underneath the propanol. And it says, what mass of oxygen gas? So I want to know the number of grams. I'll put a question mark there. How many grams of oxygen gas? Okay, so let's solve this using dimensional analysis. That is the fastest, most efficient way to do it. Number 1, write down what you want to know. I want to know the number of grams of O2. Number 2, start with the given measured quantity. I have 10 grams. Now, don't just say 10 grams. Say 10 grams of what? In every stoichiometry problem, include the formula. 10 grams of C3H7OH. Okay. And then number 3, apply conversion factors in order to cancel unwanted units. I don't want it in grams of C3H7OH, so I'm going to put grams C3H7OH in the denominator. And I convert it to moles. How do I go from grams to moles? With the molar mass. 1 mole of C3H7OH. And here's where I use the periodic table to get the molar mass of this compound. And from the periodic table, you should just plug it directly into your calculator. Don't even write it on your test. You could do it 2 or 3 times on your calculator to check yourself. You'll have 60.09 grams of C3H7OH is equivalent to 1 mole of C3H7OH. So the mass of C3H7OH cancels, and I have it in moles. But I don't want it in moles of C3H7OH, so I'm going to say times, draw a line, I'll put mole C3H7OH. And what is this step? What is the next step always in every stoichiometry problem? It's the wake up in the middle of the night screaming mole to mole ratio step. This is the most important step. Don't leave it out. And the mole to mole ratio I get from the balanced equation. I'm using this as my balanced equation, the simpler balanced equation, the one that I've circled here, using that balanced equation. And I'm going to go from moles of C3H7OH to moles of what? Well, I look over here at what I want to know. I'm trying to get it into oxygen, so I need to know the number of moles of O2. And the mole-to-mole ratio I get from the coefficients in the balanced equation. That's why you have to balance the equation. This says for every 9 moles of O2 that react, 2 moles of C3H7OH will also react. So that's the mole-to-mole ratio. And I have one more thing to do to get it to grams of O2. You can see that the moles of propanol canceled. Now I have the moles of O2. So I'm going to say times, draw a line, and put moles of O2 in the denominator. So I know the number of moles, I need to know the mass. How do I go from moles to grams? You go from moles to grams using the molar mass. Now here's where you have to be careful, because on the periodic table, we have that oxygen, which is element 8, has a mass, it says 15.9994. Okay, so what is the molar mass of O2? The molar mass of O2 is 2 times 16. It's 32 grams per mole, not 16. Don't use 16. You'll get the incorrect answer there. It's 2 times 16, which is 32. So the molar mass of oxygen is 32.00 grams of oxygen for every 1 mole of oxygen. And then when you multiply through, the answer that you will get here will be 24.0 grams of O2. It takes 24.0 grams of oxygen to completely combust 10 grams of this compound here.